There's this place, I think almost every data scientist has been there at least once. I like to call it Jupyter Notebook Purgatory.
Oh, I know that place well.
You've got this amazing model, right? It's working perfectly, the outputs are great, but it's just stuck. It only exists in that one browser tab.
Right. The classic, it works on my machine problem. It's
Us.
probably the most dangerous phrase in all of engineering.
Exactly. And the moment you want to show it to someone or, actually use it in an app, you realize you don't have a product. You have a science experiment. Just a bunch of cells you have to run in perfect order, or the whole thing just implodes.
And that's the gap, isn't it? The huge gap between data science and real software engineering. You've got the intelligence, but zero infrastructure.
Which is exactly where we're diving today. We're looking at a fantastic guide from Aman Kharwal that was just published yesterday, February 11, 2026.
And the title is Build a Production-Ready LLM API.
And I really want to stress that phrase, production ready.
Yeah, that's the whole point. We're not just, hacking together some script that prints a response. We're building a proper microservice, something robust.
We're taking a raw language model and giving it an architecture so it can handle traffic, validate what you send it, and, not fall over.
And I think the best part is the stack. This is all local.
No OpenAI keys.
No monthly subscriptions, no sending your data off to some third party. This is about owning your own stack, top to bottom.
It's what the guide calls portable intelligence.
Exactly. So the tools for this, it's a pretty modern setup. Python, of course. PyTorch for all the heavy computation.
And Hugging Face transformers for the model itself.
And then for the web server part, FastAPI.
Which, it's become the default choice for Python APIs at this point. If you're not using it, you're just making your life harder.
100%. It's fast, handles async stuff beautifully,
Right.
and the automatic documentation, it's just a lifesaver.
So let's talk about the structure. I'm so guilty of this, but when I'm prototyping, everything just goes into one giant main.py file.
The God object.
Yeah, or like final script d12.ipmynb. Kharwal says we have to break that habit immediately.
Well, yeah, if you want something production ready, you can't have spaghetti code. He pushes for what's called separation of concerns. It's standard software engineering, but a lot of ML projects seem to forget it.
So he splits it into 3 files.
3 files, .mlegend.py, schemas.py, and main.py.
Okay, so I'm thinking of these as the brain, the rules, and the server.
That's a great way to put it. You isolate the AI complexity from the web complexity.
Let's start with the brain then. demlegend.py. This is where the model lives. He wraps the whole thing in a Python class called LLEngine. Why do that? Why not just have a global function?
It's all about state management. LLMs are huge. We're using TinyLlama here, which is, 1.1 billion parameters. Even for a tiny model, that's still over a gigabyte of numbers.
And you don't want to be loading that every single time someone hits your API.
Oh, God, no. That's the load on request nightmare. Every user would have to wait 30 seconds for the model to boot up from disk. The server would just grind to a halt.
Right.
So by using a class, we can create a specific life cycle for it. There's a load model method, and you call that just once when the whole application starts.
To warm it up.
Exactly. It pulls the model weights from your hard drive, shows them into RAM or the GPU, and then, and this is the crucial part, it just stays there. It's persistent.
Just idling, waiting for work.
Yep. So when a request comes in, the engine is already hot and ready to go.
You mentioned TinyLlama, 1.1 billion parameters. I think for a lot of our listeners, they're used to hearing about, GPT-4 or Llama 3 with 70 billion. This sounds kind of weak in comparison.
Well, there are 2 reasons for it. First is just accessibility. You can actually run this on a normal laptop, right? You don't need a massive server farm. But the more important reason is that the architecture we're building is exactly the same. The code structure doesn't really change whether you're loading a 1B model or a 100B model. TinyLlama is just a great stand-in to let us build the plumbing correctly.
Got it. Now, there's one specific line of code in that mlegend.py file I wanted to ask about. Torch type, torch.bfloat16. I see this everywhere now. What's the magic here?
Yeah. That is a massive optimization. So normally, computers work with 32-bit floating point numbers, float 32. Very precise, lots of decimal places.
But it takes up a lot of memory.
A lot. bfloat16 stands for brain floating point, and it basically cuts that memory usage in half. It uses 16 bits instead of 32.
But are we losing something? Does that make the model dumber?
You'd think so, but surprisingly, not really. And here's the quick technical reason. A floating point number has 2 parts. The exponent, which is the range, how big or small it can be, and the mantissa, which is the precision, like the decimal points.
So range versus detail.
Yeah.
Exactly. bfloat1s keeps the full range of a 32-bit number, but it chops off a lot of the precision. And it turns out, for neural networks, the range is way more important than having perfect decimal accuracy.
So you get almost the same power, but for half the memory cost.
It's pretty much a free lunch in deep learning. It lets you fit a much bigger model onto your hardware without it just falling over.
Okay, so the model is loaded efficiently, but a raw language model is just a text completer, right? If I type "the sky is," it just says blue. How do we make it act like a chatbot?
That's where the chat template comes in. In the code, you see it actually formats the prompt before sending it to the model. It wraps your question in special tags.
Like it's giving it a role to play.
It's exactly role-playing. It says something like, "System, you are a helpful AI assistant. User, and then your question." Without that structure, the model might just continue your sentence. With it, you're forcing it into a conversational question and answer mode. Got it. Okay, so that's the brain. Now for file number 2, schemas.py. I called it the rules, but I think the bouncer is actually a better name.
The bouncer is perfect. And the bouncer's favorite tool is a library called Pydantic.
I feel like Pydantic has single-handedly saved the Python community from itself.
It really has. Python is dynamically typed, which is amazing for scripting, but pretty terrifying for a production service. Pydantic brings back that strictness.
So with this file, we define exactly what a valid API request needs to look like.
Correct. We make a class, generation request, and we tell it, you must send me a prompt. It must be a string, and it can't be empty.
So no null values, no empty requests crashing the whole thing.
Right. But it's more than that. We also define the other parameters, like max tokens or temperature, but we don't just trust the user to send good values.
Because they won't. Sooner or later, someone will break it.
Always. If a user sends a temperature of, like, 500, the math inside the model just breaks. You'll get garbage. So in our schema, we add constraints. We say temperature has to be between 0.0 and 1.0.
And what happens if I send a temperature of 2.0?
The API rejects it on the spot. It doesn't even bother waking up the LLM. It just sends back a clean error message saying, basically, invalid input.
That's so important. It protects the most expensive resource, the GPU, from wasting time on bad data.
It's defensive programming. Never trust user input. Pydantic handles all of that for you.
Okay, so brain is loaded, rules are in place. Now we just need the front door. Main.py, the FastAPI server.
This is the conductor. Yeah. It imports the engine and the schemas and ties it all together.
And it uses a feature called the Lifespan Context Manager. What's that about?
It's the modern way to handle setup and teardown. The lifespan function says, okay, when the server process starts, before you accept any web traffic, run this code.
And that's where we call the load model function.
Exactly. The server literally won't even start listening for requests until that huge model is fully loaded and ready in memory. It prevents that awkward delay for the very first user.
Guarantees readiness. And when you shut the server down,
the lifespan manager handles that too. Yeah. It cleans up the GPU memory, makes sure everything exits gracefully.
Okay, now for what I think is the most, the most subtle but critical part of this whole guide. The API endpoint itself. The function is generate text.
Yep.
In FastAPI, you see async def everywhere. It's kind of the whole point. But here, Kharwal just uses def. No async. What? I mean, that feels wrong.
This is the gotcha that trips up even experienced engineers. Your instinct is right. Async is usually what you want.
So why not here?
Because async is for waiting. If your code is waiting for a database query to finish or for another website to respond, async lets your server do other work while it waits. It's for I/O-bound tasks.
It's like a waiter taking another table's order while the kitchen is cooking the first one.
Perfect analogy. But running an LLM isn't waiting. It's cooking. It is pure number crunching, CPU and GPU bound work. The processor is at 100%.
The chef is sprinting.
Right. And in Python, because of the global interpreter lock, if you run a heavy CPU task on the main async event loop,
it blocks everything.
It blocks everything. If your LLM takes 5 seconds to generate text, the entire server freezes for 5 seconds. No one else can connect. It's a disaster.
So by just using a plain def, what does that do?
You're signaling to FastAPI. It sees a normal synchronous def, and it says, oh, this looks like a blocking task. I'm not going to run this on my main loop. I'm going to push this off to a separate thread pool to run in the background.
So it puts the heavy lifting in a different lane.
Exactly. The main loop stays free and responsive to handle new incoming connections. So, kind of ironically, by not using async, we make the server much more responsive for everyone else.
That is such a key takeaway. Def for compute, async def for I/O.
Get that wrong, and your API will feel broken under any real load.
Okay, so we've written the code. We run FastAPI dev main.py. What's next? How do we test it?
Well, FastAPI gives you this amazing gift called the Swagger UI.
Ah, the auto-generated documentation page.
It is. You just go to Docs in your browser and you get this beautiful interactive web page. It shows your endpoint, shows you what the JSON should look like based on your pedantic schema.
Then it has a try it out button.
Yeah. You can literally just type your question, why is the sky blue?
Yeah.
Right there in the browser, hit a button and see the live JSON response from your model. It's fantastic for testing and debugging.
So we've gone through the how. Let's zoom out to the why. I mean, why go to all this trouble with 3 files and schemas and thread pools? Why not just stay in the notebook?
It all comes back to that phrase, portable intelligence.
Expand on that.
Well, think about how companies work. The team building the iPhone app is not the same team training the AI model.
Right.
If your AI is trapped in a notebook, the app developers can't use it. But by wrapping it in a clean API like this, you create a contract. The app team doesn't need to know about PyTorch or bfloat 16 or anything. They just know, I send a request to this URL, I get text back.
You've decoupled the intelligence from the application layer.
Completely. And then tomorrow, if a new, better model comes out, you just update your lamention.y file. The API contract doesn't change. The mobile app doesn't change. They just start getting better answers.
That's the real power of this microservice approach. It's modular.
It's modular, it's scalable, it's maintainable. It's what turns a cool experiment into a real, usable product.
Okay, but speaking of scalable, we have to talk about the elephant in the room. This works for a 1.1 billion parameter model on a laptop.
It does.
What happens when I want to use a 70 billion parameter model? If I try to load that with this code, my laptop's just going to laugh at me and then die.
It won't even laugh. It'll just give you an out-of-memory error and crash.
So does this whole architecture just fall apart at scale?
The concepts don't fall apart, but the infrastructure behind it has to evolve. This is where you get into the world of what people call LLM oaks.
Okay.
When AML is too big for one GPU, you have to split it across multiple GPUs. It's called model parallelism. Maybe the first 20 layers of the network run on one machine, and the next 20 run on another.
So legend.py gets a lot more complicated.
A lot more. You'd probably stop using the basic transformers library and start using a specialized serving engine, like VLLM or TGI. They're designed to handle that kind of distributed complexity.
But what about main.py, the API layer?
And that's the beauty of it. The API layer, the schemas.py, they can stay almost exactly the same. Your mobile app doesn't care if the model is running on one GPU or a cluster of 100. The contract is stable.
That's a really powerful idea. The hard work you put into defining the interface is future-proof. The engine under the hood might change, but the steering wheel stays in the same place.
That is the entire goal of good software design.
So to just quickly recap, we took a science experiment from a notebook. We gave it a solid brain rules server structure. We optimized the engine, we protected it with contracts, and we exposed it as a clean, efficient, well-documented API.
And we did the whole thing without paying anyone for an API key.
That's the best part. It's independent, local, and totally under your control.
It's a skill that's just going to become more and more valuable, I think. Serving your own models is the next big step for a lot of engineers.
So here's a final thought to leave you with. We talked about portable intelligence and serving this API to, say, a web app or a Discord bot.
Right.
But what happens when other AIs start calling this API?
Oh, it's an interesting thought.
If you start building a network of these specialized microservices, one that's an expert at code, one that's an expert at creative writing, one that's an expert at math, and they can all communicate with each other using these clean JSON contracts, are we accidentally building the foundation for a kind of swarm intelligence?
We built the individual neurons. Now we just need to figure out how to wire them all together.
Something to think about. Thanks for listening to The Deep Dive.
Keep building.
See you next time.